Thanks for coming, everyone. Today we are going to hear from Danqi. And just to give a little intro about Danqi, Danqi Jiang is a PhD candidate in marine geology and geophysics, working with Dr. Nathan Bangs and Dr. Shosho Han. Her research explores structural interpretation, kinematic modeling, and restoration of 2D and 3D seismic reflection data to investigate fault slip behavior, deformation evolution, and earthquake hazards along the Hikurangi and Cascadia subduction margins. So go ahead and take it away.
So hi everyone. Today I'm going to present like part of my dissertation project, and it's about the characterizing outer-wedge structure of the Cascadia subduction margin using the Case 21 seismic data. So I show some pictures here. So the mouse only
You might have to click on it.
Oh yeah. Okay. No. So I share some photos I've taken before. So the first one is just the cruise lens, the lenses cruise, and it is the ship that the Case 21 seismic data set was acquired, but I was not on that cruise. So, but I also sailed with the lenses cruise, like to acquire some seismic, multi-channel seismic data set, and also some heat flow probe data set to get some hands-on experience. And the second figure is like is taken for like the streamer being tailed after the ship, but we can only see the rope here. And the third picture is the seismic lab on the lenses. And in the seismic lab, we have a lot of screens and which can show us the multi-beam bathymetry data, like the water velocity, and also the seismic acquisition and some basic physical oceanographic parameters. So the last picture was taken recently. So we had the KC21 group, the project group had like an annual interpretation meeting, and this year we had the meeting in the University of Washington in Seattle, and we had a short field trip during that meeting, and that's a picture of the members, most of the members. So here's my outline. So I will introduce my motivation and data and methods. It's about like the interpretation of the pre-stack depth migrated seismic images and also the bathymetry data. And for the result, I will cover like the structure versions segmentation of the outer wedge of the Cascadia margin, and also the fault dips with different versions. And I also calculate a long strike length of the faults. And we also interpret some of the coastal seafloor deformation and some proto-thrusts. So I will connect my result to discussion about the outer wedge strength inferred from the wedge tapers and also the dips of the conjugating faults. So as we all know, the subduction zone is where the colder, heavier oceanic plates dives beneath the less dense plates and sinks into the mantle at the convergent boundaries. So this figure shows the structure of a accretionary wedge. The accretionary wedge forms from the material, the wedge, the marine sediment being scraped off from the oceanic plate onto the overriding plate. So, and it's usually divided into two parts, the outer wedge and the inner wedge. So the inner wedge is primarily composed of the older accretionary and also the crystalline basement rock, and has a lower strain rate. And the outer wedge is primarily composed of the accreted sediment from the oceanic plate and also the deformed upper plate material. And this part of the margin experience significant active shortening and also imbricate thrust faulting, like all these thrust faults, and responds most quickly to the changing boundary conditions, and provide insight for us to the active subduction process and also associated geohazards like earthquake, tsunami, and some submarine landslides. So it's important for us to image and also investigate the structure evolution of the outer wedge along the subduction margin. So this figure is the geologic background for the Cascadia margin. So the Cascadia margin lies offshore west coast of the North America and extending over 1,000 kilometers offshore Vancouver Island, Washington, Oregon, and the North California. And for this subduction margin, the Fuca plate and also the Gorda plate subducts beneath the North American plates at a moderate rate of 30 to 40 millimeters per year. And this plate boundary is unusually quiet with respect to large earthquake, as it hosts like very little interplay seismicity being recorded. However, based on the paleoseismic record, this subduction margin also hosted like magnitude over about 9 earthquakes with recurrence intervals of 250 to 500 years. So the Cascadia subduction margin poses major earthquake and tsunami hazards to the heavily populated Pacific Northwest. So this figure from Walton's work, and there shows some along-strike segmentation of the maxwell slip behavior. So for the current locking stages, we can see that the red color represent the locking state fraction is 1, and the blue color represent that locking fraction is 0. So we can see that the interseismic coupling offshore Washington is relatively wider and broader than the region to the north and to the south of this part. And the dots represent the near plate interface seismicity. So they have different size, they have different magnitude, and also different color represent the depths of the seismicity events. So we can also see that the region offshore Washington, like this part, they have recorded less seismic events than the other regions. So, and also the purple circles represent the rupture patches for the 1700 magnitude about 9 earthquakes, and there is a large rupture patches along the offshore the Washington, and it's also kind of indicate that this region supported to rupture along a longer distance and also can recover a larger slip deficit. And finally, this part is from the interpreted along-strike extent of the turbidite events, like the turbidite events. So this is kind of take as an indication for the paleoseismicity events. So from this, the previous work conclude that the region offshore Washington has the longest reference interval for the Holocene max earthquake at about 500 years. And also, previous work, also working on the structure of the outer wedge. So they, based on the interpretation of some seismic, legacy seismic lines, first we can see that from this figure, that we can see the segmentation for the wedge morphology. And we can see that the wedge offshore Washington is wider and than the region offshore, the wedge narrows to the north and the south of the margin. And also the different color, we see that for the deformation style, the blue color represent the seaward versions of the, it's being blocked by the yeah. Yep, so the blue color represent the seaward version structure, and the red color represent landward version structure. So we can see that this section is from the region offshore Washington, and we can see that structure here is dominated by the landward vergent fault. So the landward vergent fault dips seaward, and that means the material, the honeymoon material thrust landward. And for the blue one shows the seaward vergent faults, shown by these sections. And the structure are all kind of seaward vergent faults, so it's kind of dips landward, but the material or the honeymoon moves seaward. So there is a structure vergent segmentation for for along the Cascadia margin, that we can see that the red area mainly distributed in the region offshore Washington and northern Oregon, and all the other regions like offshore the subduction margin, we can see that it's dominated by the blue one, like the seaward virgin structures. And also kind of combine that with the previous like the analysis for the Maxwell slip behavior, we can see that offshore Washington it's also with strong interseismic coupling and large slip deficits, and also longer earthquake reference intervals is correlated within the area, which we see the development of the landward virgin faults. But like, previous study also proposed that the landward virgin fault is like an atypical structure that developed in the accretionary wedge. So they are going to discuss like the mechanism, like controlling the development of the landward virgin faults. So they proposed that maybe a frictionally weak max thrust or a strong wedge, and also the presence of a seaward dipping backstop, and also like a dynamic weakening during the earthquakes can be the factors influencing the development of the landward faults. And that's from the previous work, but most of the previous interpretation is based on the seismic data with like variable resolution and also uneven coverage along the margin. And most of them are in the time sections, so significantly limiting the capability for us to analyze the wedge structure quantitatively. So here, within our newly acquired KC21 dataset, so this dataset was acquired in the July of 2021, and with the NASA's cruise. And this dataset includes like 19 change perpendicular lines covering from offshore offshore Vancouver Island to the southern Oregon. And also this dataset has like deep penetrating source, like within 4 gun arrays with total volume of 6,600 cubic inches and long source receiver offset, like 12 or 15 kilometers long streamer with 960 and 1200 hydrophones. So this enables the better image for the deeper part of the outer wedge. And also we also have some ocean bottom seismometer data, which is deployed every other lines, can provide some velocity information for the data set. And this all this 2D seismic lines is being processed by the ION company to the pre-stack depth migration migrate images and produce the higher resolution images for us. And we also use the GMRT 60 meters bathymetry grid to help us to confine like the surface features of the outer wedge structure. So this part is about the method. The first part is about like interpreting the faults from the PSDM size images. So the first 3 figures shows like some of the criteria we use to interpret fault structures. Like from the seismic images, sometimes we can identify some of the direct fault plane reflections, and also we can identify that there is some like we can kind of correlate the corresponding horizons from the hanging line forward to to see the offset of the different deformed blocks, which also show the presence of the faults. And for some region, we can identify there is some apparent change of the dipping angles of the horizons, and which also represent terminations of the horizons and showing the presence of the fault in this region. So this figure shows like some of the terminologies we use for the interpretation. So like this one and this one, it's the main faults as we defined. So the main faults represent like the primary slip surface for the thrust and fault blocks. And we divide them into 2 parts, like the seaward virgin faults and the landward virgin faults, as we kind of mentioned before. And also we interpret some of the proto-thrusts from our data. So the proto-thrusts are observed seaward of the primary frontal thrust. And they have like a very small like displacement relative to the main thrust. And also we also identify some of the normal faults and like the branches from branches from the main thrust and some back thrust, and also some not like really recent deformation, but some of the close to zero deformation from our data set. And this figure shows how we interpret the fault traces from the bathymetry data. So we've got the 60 meters bathymetry data like from, and this figure shows like the depth spatial map for the bathymetry, and we can identify some linear features from the data set, which is and this figure shows like we also use the bathymetry, but we show the depth value map, and they also can show some of the linear features that's correlated to the fault structure. So this can help us to refine like to confirm the fault locations, and we also try to correlate the fault surface features from the bathymetry data to the fault tip locations we got from the seismic images. So I took the PD10 that line as an example. So the yellow square represents the structure with a surface expression, and we can see that the location of the fault tips corresponds to the linear features pretty well. And also the red points represent some of the close to zero deformation. They also kind of show we can see a good fit between the locations of these two. So here comes my result for the first about the structure versions from our data set. So we can see that we kind of divided the Cascadia margin into 5 parts. So for the region offshore Vancouver Island, we think the structure is kind of characterized by mixed versions. And this is a 2D sections coming from that region. And we can see that for PD03, the structure is kind of leading by seaward version faults, but all the faults behind after that is kind of a landward version faults. And for the region offshore Washington, and the structure is dominated by the landward versions. And this is a long section from this region, and we can see that most of the structure here is kind of dominated by the landward version faults, and all through the outer wedge. And for the region offshore Northern Oregon, we identified as a mixed version structure again, and we can see that the different blocks are bounded by pairs of a seaward version fault and landward version faults. Like there's one pair and there's another pair. So we identify this part as a mixed version structure. And for the region offshore Central and Southern Oregon, this part, we also took an example section like from the PD13. We can see that the structure here is mainly the seaward version faults. And it's like more close to like the common, like the really classic features that we see from the Prisionary wedge. So this part is kind of dominated by seaward version faults. And there's another single line is from PD19. It's located in the southern end of the data set. And we can see that this part is kind of, we can see both the presence of the seaward version fault and landward faults. So we think it's an initiation of another like deformation style for the structure to the south. And based on our interpretation, we also noticed that there is like a difference. So we have the different colors to represent different like for extent. So the yellow line represent that the declinum is on the top of the oceanic crust, and we can see from PD06, most of the faults are reaches to the top of the oceanic crust. And like the orange line represent that a shallow declinum is present in the inner part of the outer wedge, and we can see from here from PD12. And the green line represent is a shallow detachment we interpreted from the seismic data, but it only show up in the inner part of the wedge, inner part of the outer wedge. And like the green color represent that, like shown by this figure, like PD13, we can see a shallow detachment is present all throughout the outer wedge. And like this single section for PD19, it's like similar to the structure from the PD06. They have most of the fault structure are connected to the top of the oceanic crust. So based on our interpretation of the seismic image and all the fault interpretations, we can measure the dip angles of all the faults. So we divide that into two parts. So for all the main thrust, we divide it into like the seaward version faults and the landward version faults, kind of represented by blue color and the orange color. So we can see that the dip of the main landward version fault ranges from like 26 to 70 degrees, and the main dip for them is like about 42 degrees. And like the dip of the main seaward version faults is distributed in a wider range, like from 7 to 60 degrees, but its mean dip is relatively lower than that of the landward version faults. And this figure shows so besides the main thrust, we also have interpreted some of the secondary faults. We also divide into the different directions, but they don't have like the similar patterns for the main thrust. And we can see that dips of the secondary landward version faults spans a wider range, like than the main landward version faults. So based on the measurement of the fault dips, we can calculate, like for each 2D lines, we can calculate the average dip angles for each sections. So we can get a long-strike variation of the average main thrust dips. So here it shows like the variation. So we can see that first, this figure also shows like the structural versions of the margin, that there is like some mixed versions structure offshore Vancouver Island and northern Oregon, and like the region offshore Washington is dominated by the landward version faults, and the region offshore central and southern Oregon is dominated by the seaward version faults. And the background color also kind of related to the extent of the faults. So as I kind of mentioned before. So also we can see that the landward version faults has a relatively larger dip angles than the seaward version faults. And for landward version fault, they have a relative constant value across the different sections, except for that single point from the PD19. But for the seaward version faults, they have like displayed a greater variability in the average dip angles across different dip lines. And this figure shows like, so we have calculated the average dip angles for each sections, but we can also see how the dip angles varies along the dip direction for each section. So here we show two of the examples for like the blue line, the blue pentagram shows like the dip angles from PD13. So it's the region for the seaward version faults. So we can see that the dips of the seaward version fault increase with the distance landward of the deformation front. So it's like the typical deformation style that we see from the accretionary wedge, and as the material being accreted to the wedge, the material can rotate, which increase like the fault dip angles towards the landward. And the red point shows all the dip angles that we have from PD06. So it's a region of the landward version fault zone. And we can see that dip angles is relatively constant throughout the outer wedge. And take apart, like that's the point for the primary frontal thrust, and that's kind of like it's kind of like more like a secondary fault. So for all the other points, we can see that they have relative constant dip angles, and also they are evenly spaced, distributed along the dip direction of the structure. And here I will show the results for like the along strike length of the faults as we interpret from the bathymetry data. So this figure shows like all the locations of the 2D seismic lines, and also I interpreted like fault traces by the white lines, and also the different points represent like the fault tip locations that we interpret from the seismic images. And this is a zoom in images from the region offshore Vancouver Island. So that's from like our first version of the interpretation. So it's kind of preliminary results, but we still can see some patterns from the interpretation results. That is for the region offshore Vancouver Island, we interpret like about 73 fault chases, and most of them are kind of located. The length of the faults are distributed from like 5 to 30 kilometers. So for this region, we have a mean length about like 17 kilometers. And the second part is the region offshore Washington, and we can for this region we interpret like about 63 fault chases, and they are kind of we can see that they kind of span a wider range than the fault chases we interpreted from the region offshore Vancouver Island, like from 5 to 55 kilometers. So they have a relative larger mean length than that from the region offshore Vancouver Island, which is about 22.56 kilometers. And this figure shows the zoom in the interpretation from the region offshore Northern Oregon. And they also have longer linear features from the bathymetry data. And here, because of the region is kind of smaller than the other area, so we only interpret like 28 fault chases, but they also have a really relatively large mean length for the fault chases, about 21.09 kilometers, which is similar to that of the region offshore Washington. And the last region is about the region offshore Central and Southern Oregon. And for this part, because of the low resolution from the bathymetry data, and also this part of the margin, we also experience some of the submarine landslide, which also covers some of the surface features for the faults. So, but we can still, but in general, in this region, we didn't identify like some really long linear features like we see from the region offshore Washington and Northern Oregon. And for this region, we also integrate like about 100 like fault chases, and we can see that the mean length for this region is pretty kind of small, shorter than that of the region offshore Washington and Northern Oregon, which is only about 14.68 kilometers. So here, the information that we get is that the region offshore Washington and region offshore Northern Oregon, they have like a relative longer fault chases than the region offshore Vancouver Island and the Central and Southern Oregon. And afterwards, we want to use this length of the faults to help us to estimate the geohazards. And this is the result we got, like showing by the interpretation of the close to seafloor deformation. And here we can see that, and most of them are, here's the examples of the close to seafloor deformation. And most of the deformation that we interpret is the branches from the main thrust. And here, some of the features we can see the the direct fault reflection lines, but some of the other we can also see there is some deformation from the horizons, which we can help us to interpret the fault structures. And here, like this figure shows like the along strike distribution of the close to seafloor deformation. And the key point for here is that the close to seafloor deformation is not solely concentrated along the deformation front of the outer wedge, but to the south we can see that they spans a wider range and towards the landward of the structure. And the last part of the result is about the protothrust. So here these two figures shows the examples of the protothrust we interpreted. And the protothrust is kind of most of protothrust land like located seaward of the primary frontal thrust. And they have really small displacement, and also they don't have like a obvious like surface expression that we can interpret it from the bathymetry data. So here we also, this figure shows like the along strike variation of the average protothrust dip angles. But we can see that the dip angles of the protothrust have a large variability along the strike. But from these figures, we can see that most of the protothrusts are observed offshore Vancouver Island and Washington. And there's only like 2 points that we get the interpretation of the protothrust for the region offshore Central and Southern Oregon. And also we measure the dip angles for the protothrust. And they kind of have the similar feature that we got from the mass thrust. It's that the seaward dipping, like shown by the green line. So the green part shows the seaward dipping protothrust. And they have like slightly steeper dips with a mean dip of 47 degrees than the landward dipping ones, which with a mean dip of about 37 degrees. So based on our interpretation, we mainly got the dip angles of like the protothrust and also the mass thrust from the seismic interpretation, and also we got the like the wedge morphology of the structure. So here we want to use like the wedge tapers and also the contributing faults to help us to infer the outer wedge strength. So here's kind of really famous papers from Davis at 1983. So this schematic diagram shows like a wedge of material being subject to the horizontal compression, and also on the verge of like Coulomb failure everywhere of the wedge material. So based on the force balancing, like for the gravitational body force, like for the wedge material, and also the pressure for the water overburden, and like the resistance for and the frictional resistance to sliding along the basal detachment, and also the part of the like the compressional push. So previous work, they kind of come up with a relationship between the wedge tapers alpha plus beta to the frictional strength, and also the pole fluid pressure ratio of the wedge material, and also the basal detachment. It's shown by this equation. So there's a relation between alpha and beta, and the mu and mu b lambda and lambda b. So mu is kind of take effect in the parameter k that we have defined by b. So also from our data set, we can get like the wedge tapers like alpha and beta from our seismic data, but we need to make some assumption for all the other full unknowns, because we cannot get full unknowns from only two known parameters. So also based on their work, they have like to make two assumptions. Like from this figure, they kind of like they have assumed that the basal dip beta at 6 degrees, and like the mu b is about 0.085. So for each different values of mu, like from 0.885 to 1.2, we can get a relationship between the surface slope alpha and like the fluid pressure ratio lambda, and they also assume that lambda equals lambda b. And this figure shows that when we assume that they kind of given a value for mu and mu b, so they assume that mu equals 1.03 and mu b equals 0.85, and they also assume that lambda equals lambda b. So for different values of lambda and lambda b, they can get a linear relationship between the surface slope alpha and the basal dip beta. And here they kind of plot the data they got from different like subduction zones to submarine wedges, and to see how the lambda value varies for different regions. So here's our result about how to, and so like here is the examples of the wedge tapers calculation from our data set. So we interpret the locations of the seafloor. And that's the location of the basal detachment. And we can define the extent of the outer wedge by ourselves, so we can measure the dip angles like for the alpha and beta from within the range that we defined. But we also kind of measure the alpha and beta value within within the range of like about every 10 kilometers. So from 10 to 50 kilometers, we can measure the dip angles for alpha for the surface seafloor and the basal detachment. So here's the results that we can see. The red thicker line, it shows the result for the alpha angle and the beta value. And like the color, the other lines from like dark blue to the light yellow kind of represents the results we calculated with the extent from 10 to 50 kilometers. So like for the region the region, like within only 10 or 50 kilometers, only 10 kilometers, they have a large variation or from the manually defined extent. It's kind of related to like the different extent of the wedge along the strike. So here is this figure shows the alpha and beta value we finally deployed to infer the outer wedge strength for our study. So we can see that the blue lines represent the alpha value from the 2D lines across the Cascadia margin. And we can see that for the region offshore Vancouver Island to offshore Washington, and this is the part from offshore Northern Oregon, they have a relatively low value for the alpha angle, and it's about 2 degrees. But when it goes to the south, as we can see also from the wedge morphology, the alpha value increase like to about 4 to 5 degrees. And the red line shows the result for the beta value. And we can see that also for the region, like from offshore Vancouver Island to the Northern Oregon, it has a relative lower value, about like 4 degrees for the beta. But when it goes to the south, we can see that from the seismic data, it's because there is a step down for the basal decrement that can increase the dip angles for the beta in this region. So this figure shows like, so we kind of assume that we have a discussion like about like how we can kind of define the mu and mu b value for our data. So we define the mu b as 0.4 for our data, and also we assume that lambda equals lambda b, and it's 0.7. So and also combined within the alpha and beta we measured from our seismic data, then we can get like the value between mu over mu b. That is kind of the stress contrast for the frictional strength of the wedge material. So we can see that stress contrast for the wedge material offshore Washington is about 1.5 times larger than the surrounding areas, like for the region offshore Vancouver Island and Northern Oregon. And the stress contrast to offshore Central and Southern Oregon is kind of going really low. It's only about 1.3. So that means kind of the stress contrast of offshore Washington is kind of relatively large than other area. And this figure, like for this figure, we assume that mu b equals 0.4 also, but we also define a mu value for it. So we define mu equals 0.5, and then say assume that lambda equals lambda b. So we plot all the alpha and beta value we get from each sections onto this figure, and the different color represent the locations of the different 2D seismic lines. So the green points represent the data point from the region offshore Washington, and we can see that they have a relative large lambda value, which is about like 0.97, which means they have a relative large pore fluid pressure ratio. And for the region offshore, like the blue point, it represents the region offshore Vancouver Island, and the red point represent the region offshore Northern Oregon. They have relative similar value, which is about like 0.9, and with that is kind of relative a little bit lower than that of the region offshore Washington. And the yellow point represents the table value we got from the region offshore Central and Southern Oregon, and they kind of span a relative wide ranges, but they are all kind of smaller than that of all the other regions. So we think that the region offshore Washington, they kind of have like a relative strong stress contrast for the wedge material. Also like the pore fluid pressure in this region also maybe take effect for the outer wedge strength. And this figure shows like how we can infer the outer wedge strength from the depths of the conjugating faults. So previous work, they assumed that the observed faults from the seismic data are formed as fresh Coulomb failure, present as like pristine and coeval conjugating faults. So, and like the coolant failure criteria is most easily satisfied along the surface of the optimal, which is kind of related to the angle of the internal frictional. So here, if we can know like the angles between the angles for the shallow dipping forward thrust and also the steeply dipping back thrust, then we can get the angles like the psi b, which is the angle between the maximal compressive stress and within the basal detachment. Then we can get the value for the phi value, which is internal friction. So we can use the dip angles of the congenitive force to infer the strength of the outer wedge. So this slide shows like the examples that we took for the inference. So this is the section, is the cross section from PD06, and we interpret a conjugated force like this force. We take this force as the deeply dipping like landward version force, and this one is the seaward version force. And we also use that to calculate for the outer wedge strength, but because it's hard to identify whether the conjugated forces are coeve or pristine, so the calculation result we got from the conjugated forces is not so representative. So we are thinking about using the dip angles of the protothrust, because we also identify some of the protothrust which dips two directions from the some of the 2D seismic lines. So we are using the dip angles of the protothrust to do the inference. So based on the dip angles of the protothrust, we can get the parameter as mu over mu b prime. Here the parameter is different from mu over mu b. It's because it also includes effect of the whole fluid pressure onto the parameter. So we can see that the blue lines are the result from the inference of the wedge tapers, and the red points represents the result we get from the protothrust. And we can see that they have the patterns of the around stress variation of the stress contrast are similar, like from the red one and the blue one. But there's some offset of the mu over mu b, we can see that in this part, the red point, they have some offset from like the blue lines. So we think that that may be because the effect of the pole fluid pressure take effect in the region offshore Vancouver Island and Washington. So here comes my conclusion. So what's the key point of the this project is that we can know that structure of the outer wedge offshore Washington, like this part, is dominated by landward vergent faults, and landward faults, they have a relative larger dip angles than all the other regions and relative constant value. And but also the outer wedge offshore Washington, they have a larger the frictional stress contrast, which is it's kind of like the outer wedge offshore Washington. They has a larger physical stress contrast of between the wedge material and the basal detachment, and which includes both effect of the frictional strength and also the pole fluid pressure. And this page is about my future work. So I'm not writing up a manuscript for the publication based on the above results, but my next project will be about the outer wedge, like 2D structural restoration. Because I've already interpreted all the four structures, then we will take some of the 2D seismic lines which we can identify some stratigraphy. Then we can use that to do some 2D structural restoration to see like how the structure varies during the deformation history, like between the area like offshore Washington and and the region offshore Oregon. That's all great.
Do you have any theories on why the faulting behavior changes, like what external drivers are, or why it changes from north to south?
So yeah, like I mentioned
I
from,
might have missed that.
yeah, but yeah, that's kind of, because from my introduction pages, I've mentioned that previous work, they also kind of discussed like why there's some really atypical like language faults in this region offshore Washington. Like, so they kind of raised like these parameters, like so they kind of, it's more like either the max thrust is frictionally weak, or like the wedge material is relatively strong than the max thrust. Or they have some of the previous work also attribute that to there's a seaward dipping backstop from between the outer wedge and the inner wedge. And also like the dynamic weakening during the earthquake. And based on our kind of work, we think at least there's kind of for the region offshore Washington, they have a relative like large stress contrast between the wedge material and like the base of detachment, which kind of support what they say from these parts.
Is it related to, there's like an accreted oceanic aspect inside that area, so?
I feel like for that area, it's kind of more related, they have different like sediment inputs, like for different regions. And they, like for the region offshore Washington, they have like rapid sedimentation during the glacier, but like for the southern region, like the region offshore, the Central and Southern Oregon, this part we don't see like a lot of the material, but we could also identify a lot of landslides in that region. And also recently, me and Susu, we are kind of trying to recheck our interpretation, and we find that that region also we kind of miss some of the normal faults in that region, which kind of show different like stress states for that part.
Is there any correlation between the lengths of the faults that you measured on the surface and how much displacement there is on them?
For displacement, I'm trying to, but I haven't done like the correlation for the stratigraphy, so I haven't got an exact number for the displacements along the faults. But we are thinking about maybe we can have the length of the faults along the strike, but also the length along the dips, along the depth domain of the fault, and we can use that maybe for the geohazards like assessments. But for displacement, maybe next when I got the stratigraphic correlation done, I can tell you that. Yeah.
Well, it just stands to reason that the ones that have more displacement will also be longer along the strike.
Mm-hmm. We need to check that later.
Were the landward faults steeper just because of those mechanics diagrams you showed at the end, or is there another reason that the landward faults were usually steeper than the seaward faults?
Haven't. Kind of, but I feel like now for my work, I'm kind of trying to, I observe this phenomenon that landward version faults have steeper dip angles and seaward version faults, and I wanted that to use that to kind of to infer like this region may have like a strong, like a larger stress contrast between the wedge and like the basal detachment. But I feel like these two parameters, they are kind of affect each other like interactively. So I cannot say that really detailed exactly like which one take effect to increase which. Yeah.
Well, if you go back to your slide showing the stress, I think that the more circle one, you can see that the landward version fault is steeper than the seaward version fault that is expected because of your largest principal stress is like plunging seaward, right? And then you're expecting to see the conjugating fault like formed like about 45 degrees from that. So the landward version fault is expected to be steeper than the seaward version fault. So Danqi's work, now we have this depth migrated images previously in this region, most of the images are in two-way travel time, the vertical axis. So that limited our capability to determine their true geometry. Now we have this depth images, so we can measure their angles and, know it quantitatively. So that confirms like this is indeed like this landward vertical is like, steeper than the seaward vertical. And from this angle, we can also calculate the principal stress direction.
Awesome. Well, let's thank Danqi one more time. Return next week for a talk by our very own Peter Miller. Thanks, y'all.